At 7:30 in the morning, a man named Kenneth Arkin drives out to the middle of the bridge and holds up an anemometer. 38 miles an hour. He writes it down. The deck is bouncing, and he notes that too. And he notes that it isn't much. The bridge has been doing this since the day it opened. Everybody who works here has stopped finding it remarkable. A little before 10, a professor from the University of Washington sets up on the roadway and takes his own readings. The bridge is riding its usual wave, 36 cycles a minute. The wind has come up to 42. He has a camera with him because he's been hired to find out why this bridge won't hold still. A few minutes later, the motion changes. It doesn't build. It switches, all at once, and the span starts to roll. By a little after 11, the middle of it is in the water. The man with the camera got most of it on film, and that film became the most watched piece of engineering footage ever shot. It's been playing at the wrong speed for 26 years. My name's Ray Callahan. I read these out of the record. For this one, the record is a single document. The report the Federal Works Agency published in March of 1941, 287 pages, signed by Othmar Ammann, Theodore von Karman, and Glenn Woodruff. It's linked below. You can check every number I give you. Here's what I'll show you. First, the one thing about this bridge that had never been built before, and the man who measured it wrote it down and recommended the fix. Second, the 4 months it spent open to the public in a condition this report calls unsatisfactory for traffic. And third, the film, what it actually shows, which is a different thing from what you've been shown. And I'll tell you now that nobody died here. That's the strangest fact in this story, and it isn't a mercy. It's timing. This report clears everybody. In its own summary of conclusions, it says the bridge was well designed and built, that the failure came from forces nobody realized would matter at this size, and that the designer's expectations were unquestionably justified. And then it attaches, as appendices, the letters and reports of every man who had the standing to stop the job. I've read them. They all saw it. They all wrote it down. And every one of them handed the decision back to the same person. So the question I want to hand you is about the difference between a verdict and an attachment. The verdict says no one was at fault. The attachments are still in the file. Leon Moisseiff was, in 1938, one of the most respected suspension bridge engineers alive. And that's the report's own assessment of him, not mine. He'd been engineer of design in the New York Department of Bridges from 1897 to 1914. He worked on the Delaware River Bridge at Philadelphia for 6 years. He was consulting engineer for the Port of New York Authority, and after that for the Detroit River Bridge, the Golden Gate, the San Francisco-Oakland Bay Bridge, and the Whitestone. His reputation rested on a piece of mathematics called deflection theory. The short version is this. In a suspension bridge, the cables carry the load, and as the cables take that load, they change shape, and that change in shape helps carry the load too. Once you can calculate it, you find the deck doesn't need to be as heavy as engineers had been building it. You can make it lighter. You can make it thinner. And thinner is cheaper and better looking. So for 30 years, every time Moisseiff's numbers said a deck could come down in size, it came down and the bridges stood. That's the record he was carrying into this project. 3 decades of being right about exactly this. I'm not handing you a villain. The document doesn't support one, and I've looked. What it supports is a man whose method had worked every single time, walking up to the one bridge where it wouldn't, with nobody in the room whose job was to say so. Here's the thing to watch. It isn't the wind, and it isn't the steel. It's a ratio. The Tacoma Narrows Bridge had a main span of 2,800 feet, and it was 39 feet wide, measured from cable to cable. Divide one into the other, and you get 1:72. 1938 had a lot of long suspension bridges to compare that to. The Delaware River Bridge was 1:19.7. The Ambassador, 1:31. The Whitestone, 1:31. San Francisco Bay, 1:35. The George Washington, 1:33. The Golden Gate, The longest span on Earth at the time was 1 to 46.7, and Tacoma was 1 to 72, not at the edge of what had been done, off the end of it by a factor of about 1.5 on a bridge nobody had built the equivalent of anywhere. Now, that table I just read you isn't something historians worked out later. It's in the file. A man put it there in September of 1938, 3 weeks before the contract was signed, and he wrote a recommendation underneath it. The Reconstruction Finance Corporation was buying the bonds on this bridge. Before it handed over the money, it hired an engineer named T.L. Condren to review the plans. His report is dated the 21st of September, 1938, and it's Appendix 4 of the Federal Report. This is what he wrote. In view of Mr. Moisseiff's ability and reputation, I hesitate to make any criticism of the structural design. But from a practical standpoint, I would feel that the width of this bridge relative to the length of spans was open to criticism, particularly since it was without precedent. Without precedent. He found the one thing about this bridge that had never been done, and he found it before anybody poured concrete for the anchorages. Then he built the table. 7 bridges, 7 ratios, Tacoma alone at the bottom. And then he made a specific, costed recommendation. Widen the superstructure to 52 feet. That would give a 42-foot roadway with 2 sidewalks, and it would bring the ratio to about 1 to 54, back inside the range of every bridge that was standing. He wrote that the cost would go up considerably, and then he wrote this. The additional cost would certainly be justified, and he wrote when to do it. I recommend that serious consideration be given to the possible increase in the width of this structure before the contract is let or work begun. That's the whole thing. The defect, the fix, the price, and the deadline in one document from the man the lender hired to find exactly that. 4 paragraphs later, in the same report, he gives it back. In view of Mr. Moisseiff's recognized ability and reputation and the many expressions of approval, I feel we may rely upon his own determination of stresses and deflections. And in his conclusions, he says it plainly. I do not pretend to be qualified to analyze and check the design of the long-span suspension bridge. He wasn't the only one. The Washington Toll Bridge Authority had appointed its own board of consulting engineers. Their report went in on the 31st of August, 1938. The federal investigators quote it. The board commented at length on the design, and then, in their own words, owing to lack of time, had not attempted to check any of the calculated stresses and deflections. They did give an opinion on the width. On a ratio of 1 to 72, the board wrote, in our opinion, this feature of the design should give no concern. And then, we have full confidence in Mr. Moisseiff. Above them was the federal money. The Public Works Administration put up a grant of $2,700,000 and a loan of $3,300,000, approved on the 27th of June, 1938, later raised to $6,400,000 in total. On what its engineers checked, the report is blunt. The Public Works Administration relied almost exclusively on the reliability and integrity of the owner's engineers and architects. And there's a statement in Appendix 3, written in December of 1940, by a PWA officer named Madigan, explaining why. The Public Works program was running more than 16,000 projects at a cost above $4 billion. Going further than they went, he wrote, was definitely impractical. I want to be fair to him. At that scale, he's probably right. Nobody was going to staff a bureau that could independently check 16,000 designs. The hole in the system wasn't a lie anyone told. It was arithmetic. There's one more page, and it's the one I keep going back to. While Condren was doing his review, he wrote to Moisseiff directly, and Moisseiff answered on the 14th of September. In that letter, Moisseiff describes his own bridge. He writes that it is very narrow for the length of its center span. He gives the ratio himself, 1 to 72, and then he assesses it. For a bridge of such horizontal slenderness, the obtained stiffness is rather satisfactory. Condren read that sentence the same way you just did. Here's his note on it, in his own report. There seems to be some question even in his mind as to whether the obtained stiffness is other than rather satisfactory. He caught the hesitation inside the word rather. He wrote it down, and he signed off anyway. The bridge opened to traffic on the 1st of July, 1940. It moved from the beginning, not on bad days, on ordinary ones. The construction crews had seen it while they were still hanging the deck, and it got the nickname before the public ever drove across it. The federal report puts the 4 months on the record in one sentence, and I'd like you to hear the whole thing. The undulations continued after the structure was completed and opened to vehicular traffic on the 1st of July. And before the 7th of November, those oscillations, in the report's words, were of such magnitude that the structure could not be considered satisfactory for traffic. It carried the public for 129 days in a condition the federal government would later describe that way. They worked on it the entire time. Hydraulic buffers, tie-down cables anchored to 50-ton blocks on the shore. The cables snapped. They kept going. And they brought in the University of Washington. Frederick Farquharson built scale models and ran them in a wind tunnel, and by November he had recommendations on the table and a bridge that was still moving. 3 days before it fell, the project engineer, L.R. Durkee, wrote a letter summarizing what they'd learned. It's quoted in the body of the report. I'm going to read you 4 of his 6 points. Point 1. Motions of considerable magnitude, with amplitudes as high as 48 inches, have been observed with wind velocities as low as 3 or 4 miles per hour. Point 2. The violence of motion is not necessarily proportional to the velocity of wind. Point 3. The bridge had also stayed perfectly still, at times in winds anywhere from nothing up to 35 miles an hour. Point 6. Altogether, 7 different motions have been definitely identified on the main span of the bridge, and likewise duplicated on the model. Read those together. 4 feet of movement in a 4-mile-an-hour breeze. No relationship between how hard the wind blew and how hard the bridge moved. 7 separate ways for it to go, all of them reproduced in a laboratory. That's the state of knowledge on the 3rd of November, 1940, written down by the man running the job. Nothing in that letter says the bridge is about to fall. I want to be honest about that. What it says is that they'd stopped being able to predict it. Kenneth Arkin is woken up by the wind at 5 in the morning. He drives out to check the temporary guy cables. A fresh wind from the south, and he notes it's having very little effect. He goes home, has breakfast, and comes back to work at 7:30. That's when he goes to mid-span and takes the reading. 38 miles an hour. The bounce is noticeable and no great magnitude. Farquharson arrives with his camera. Just before 10, he's got a series of observations and photographs, and the bridge is in what the report calls the usual vertical motion, 36 cycles a minute, running as at least 9 waves along the span. He measures the wind at 42. And then, in his words, a few minutes later a violent change in motion was noted. This change appeared to take place without any intermediate stages and with such extreme violence that the span appeared to be about to roll completely over. The motion that a moment before had been 9 or 10 waves along the deck had shifted almost instantly to 2. The bridge had stopped going up and down and started twisting. The report's 5th conclusion names what let go. It appears reasonably certain that the first failure was the slipping of the cable band on the north side of the bridge to which the center ties were connected. This slipping probably initiated the torsional oscillations. A band clamped around the main cable at the center of the span, holding the ties that kept the deck and the cable moving together. It slipped. After that, the deck and the cable were free to argue with each other. There was a car abandoned out on the main span. An engineer named C.M. West saw it when he got to the bridge, and he wrote down what the deck was doing around it. pitching about the long axis to about 30 degrees each way from horizontal. 30 degrees each way. And then West walked out onto it. He wanted to see whether the concrete was breaking up. He got as far as a point just west of Tower Number 5 and found the sidewalk slab sliding back and forth along the girder about 2.5 inches at a time. He decided it wasn't wise to go further, turned around, walked off, and reported to Eldridge at the toll house. Then 700 feet of deck came out of the west quarter of the main span and went into the water. And here I want to give you West's own sentence, because I don't think anyone has written a better one about this bridge. After that section fell, the motion eased. He thought it might stop. In his words, it seemed as though the motion might die out completely and the bridge remain in that condition. However, as I was standing and thinking of that possibility, the remainder of the deck started to fall into the narrows progressively as the suspender ropes snapped. Nobody was killed. The bridge had emptied itself in the 20 minutes before it went, and the people who'd been on it walked off it. The federal report doesn't mention the dog. Engineering reports don't. The newspapers did, and the story that survived 90 years is that the only living thing left on that span was a car with an animal inside it that wouldn't be coaxed out. So here's the footage. You've seen it. It's been in physics classrooms for 85 years, and it is very probably the most reused piece of engineering film in existence. There's a problem with it, and the problem isn't the bridge. The men filming that morning were shooting 16mm film. On 16mm, silent film ran at 16 frames a second, and sound film ran at 24. This was silent. It ran at 16. In the year 2000, when the film was transferred to video, the technicians assumed 24. Every 4 frames of film became 5 frames of video. The original had 80 frames for one full swing of the bridge. The video has 100, which means the bridge you've watched is moving about 50% faster than the bridge those men were standing in front of. The film is fine. The video is wrong. And now I'll show you the part that I find hard to get over. The correct number was already printed in the federal report in 1941. Page after page of analysis, and then this sentence about the twisting that took the bridge down. The frequency was, according to reports, 14 cycles per minute at first and changed to 12 cycles per minute after the structure began to fail. On the same page, the board's own calculation for that mode comes out at 12 cycles a minute exactly. 12 in the document, 18 in the video. For 26 years, students have been timing the wrong one. And there's a reason the film ended up carrying the number at all. Farquharson wrote it down himself that morning when the motion changed. The frequency was not checked at this point, but a photographic record was taken from which this data may be taken after processing. He didn't measure it. He filmed it and said the film would tell them. The film did tell them. Then somebody copied the film wrong, and the copy is what got taught. If you'd rather not take anyone's word for any of this, there's a way to check it yourself, and it's the method the physicists used. Concrete falling off a bridge falls at the speed gravity makes it fall. That's fixed. Time the debris going into the water, compare it against what gravity allows, and the film tells you its own speed. That's the whole trick of this channel in one example. The record was right, the copy of the record was wrong, and almost nobody went back to the record. Amann, von Karman, and Woodruff signed their report on the 28th of March, 1941. Conclusion 1 says the Tacoma Narrows Bridge was well designed and built to resist safely all static forces, including wind, usually considered in the design of similar structures. Conclusion 2 says it was not realized that these aerodynamic forces would affect a structure of this size. Later on, they write that the designer's expectation about the bridge's rigidity was unquestionably justified. Read on its own. That's an exoneration, and it's a fair one. The physics of torsional flutter at that scale was genuinely not understood in 1938, and I'm not going to pretend otherwise. And then there are the appendices. Same report, same binding, Appendix 4, where the lender's own reviewer identifies the one unprecedented feature, prices the fix, sets a deadline, and defers. Appendix 3, where the federal agency explains it never checked designs. And the board of consultants who didn't check the calculations because there wasn't time and had full confidence anyway. Nobody hid any of this. It was published in 1941 by the government, attached to the finding that nobody was at fault. It's been sitting in the same file for 85 years, 300 pages behind a conclusion that most people stop at. Here's the question I said I'd hand you. Condren did everything the system asked of him. He read the plans, he found the flaw, he named it, he priced the correction, and he put it in writing before the contract was signed. Then he wrote that he wasn't qualified to check the design of a long-span suspension bridge, which was true, and he deferred to the man who was.
So what exactly was he for? If a reviewer's job ends where his own expertise ends, and the only person with the expertise is the person being reviewed, then the review is a formality with a signature on it.
That's the shape of the whole. Everyone qualified to object had a reason to defer, and every one of those reasons was a good one.
I'm Ray Callahan. On this channel, we read the document before we tell the story. Every page I quoted is in one PDF, linked below.
Page 139 for the design wind speed, page 164 for Condren, page 212 for the frequency. Go argue with me in the comments with the page number. That's the good version of this. And the next one. In December of 1967, a suspension bridge over the Ohio River dropped into the water at rush hour with no warning at all, and 46 people died. What brought it down was a crack inside a single link of the chain that held it up. Every bridge in this country is inspected the way it is today because of that crack. That's the next report. Subscribe and I'll read it with you.